All right, let's jump right into this explainer and crack open our advanced practice toolkit. Because let's be honest for a second, tutorials kinda lie to us. While basic algorithms work perfectly on those pristine textbook datasets, real-world data, it's a completely different beast. It is messy, it's horribly imbalanced, and it is deeply unforgiving. So today, we're going to walk through the exact, highly practical techniques that data scientists rely on when the standard out-of-the-box methods just aren't cutting it. Here is our roadmap for the next few minutes. We'll be rapidly tackling fixing imbalanced datasets, combining models, taming neural networks, handling multimodal data, transfer learning, and finally, algorithmic efficiency. Section 1. Fixing imbalanced datasets when one class dominates. We'll start with a massive hurdle in data preprocessing. So imagine you're hunting for credit card fraud in a massive e-commerce system. Because genuine, perfectly legal transactions are just so overwhelmingly frequent, your model faces a huge temptation. It risks misclassifying those rare fraudulent examples just so it can get the massive majority of normal transactions right. Think about it. If your model blindly guesses legal every single time, it boasts a 99% accuracy. Sounds amazing, right? Wrong. It completely fails at its actual job of catching the bad guys. And that brings us to our first real solution. In a standard setup, a model might completely miss those rare minority cases. But if you define a higher cost, basically a heavier weight for misclassifying that minority class, an algorithm like support vector machines will actually move its decision boundary. It actively shifts its focus to ensure it catches those rare fraud cases, even if it means accidentally misclassifying a few normal transactions along the way. Now, what if your chosen learning algorithm just doesn't allow you to assign different weights to classes? Well, in that case, you've got to manipulate the training data itself. You can do this by either oversampling, which literally makes multiple copies of the rare class examples so they have a much louder voice, or undersampling, where you randomly delete examples from the dominant majority class to level out the playing field. Or you can pull out the heavy machinery. Algorithms like SMOTE or its cousin ADASYN don't just copy existing data, they literally invent new synthetic data points. Think of it kind of like a digital police sketch artist. It looks at the known suspects and draws plausible new faces right in those specific areas where the minority class is scarce. It is a fascinating way to flesh out a dataset. Section 2. Combining machine learning models, the ensemble approach. So what do you do when a single, very strong model just isn't delivering the performance you need? You team them up. But here's the catch. You want to combine uncorrelated strong models. Think about pairing an SVM with a random forest. Because they learn in totally different ways, their blind spots won't overlap. You can combine them in 3 main ways: by averaging their prediction scores, taking a simple majority vote, or using a highly effective technique called stacking. Think of stacking like a really smart manager listening to a team of experts. Your base models, the experts, look at the data and make their individual predictions. Then, instead of just taking a simple vote, you feed those predictions into a brand new metamodel. This metamodel learns exactly which experts to trust and when, ultimately making a much sharper, highly accurate final decision. Moving right along to Section 3, Taming Neural Networks, Battling High Variance. Let's shift gears to deep learning. Your incredibly powerful neural network is severely overfitting, meaning it perfectly memorizes the training data but totally bombs on new validation data. To fix this, you need advanced regularizers. First, you might use dropout, temporarily blinding certain nodes during training to force the network to be robust. Next, batch normalization standardizes data between layers to keep things stable. Then you have early stopping, literally slamming the brakes on training the exact moment validation performance drops. And if you're working with images, data augmentation is huge. You randomly zoom, rotate, or flip your images to artificially create more training data and stop that memorization in its tracks. Section 4. Handling complex multimodal data. Text meets images. Our fourth roadblock hits when your model's inputs aren't uniform. You're dealing with multimodal data, meaning you might need to process a photo and its descriptive text snippet at the exact same time. The secret here is figuring out how to merge these different data types. With deep learning, you actually build 2 separate subnetworks, say a CNN to read the image and an RNN to read the text. Once each subnetwork distills its input into a mathematical embedding, you literally glue those 2 vectors together into one massive, wide feature vector. It's how you force your model to see the image and read the text in the exact same breath.
Which brings us to Section 5, the power of transfer learning, recycling knowledge. Say you're tasked with building a complex classifier for thousands of specific company documents, but there's no way you can afford the time or money to manually label millions of examples from scratch. The secret? Transfer learning. You recycle. Imagine taking a neural network that already learned the intricacies of human language from millions of Wikipedia pages. You take that model, freeze its core layers so it doesn't forget its foundational knowledge, strip off its final classification layers, and snap on new ones adapted to your specific documents. Then, you only retrain those new final layers using your tiny dataset. It is an absolute game changer for saving time and money.
And finally, Section 6, writing efficient algorithm code, Python optimization.
Look, we've covered the math and the architecture, but a machine learning model is completely useless in production if it takes a century to run on your servers. Efficiency is non-negotiable. Computer scientists use big O notation to measure how algorithmic complexity scales. Relying on nested loops creates O of n squared complexity. And let me tell you, when processing the massive scale of modern big data, an O of n squared algorithm won't just walk, it will absolutely crawl. You always want to aim for linear time, or even better, log n whenever you can.
So from a practical standpoint, optimizing your Python code is a must. Stop using slow for loops and start leveraging NumPy for lightning-fast matrix operations. If you're just checking if an item exists in a collection, please stop using lists and use sets. They are designed specifically for fast lookups. And perhaps most importantly, stop writing custom scientific code. Use libraries like scikit-learn and SciPy. They were built by experts and have operations implemented in C for absolute maximum speed. So, as we pack up our advanced toolkit today, I want to leave you with a bit of a challenge. Audit the models you're building right now. Are you just writing fragile code that works perfectly in a pristine, safe Jupyter notebook? Or are you actually engineering rugged, real-world solutions that can survive the imbalance, the noise, and the massive scale of reality? The choice is entirely yours. Keep building and keep learning.